Imagine you want to travel from one side of the universe to the other. The universe is enormous. Even light takes billions of years to cross it. If you tried to travel in a straight line, you'd never make it in a human lifetime. Not even close. But what if space itself could fold? What if you could punch a hole through the universe and step out on the other side? That idea has a name. It's called a wormhole. And it's not just science fiction, it comes directly from Einstein's equations. In this video, we're going to understand exactly what a wormhole is, where it comes from, and why it's so hard to actually use one. Let's start with the basics. Before we can understand a wormhole, we need to understand what space actually is. We often imagine space as empty and flat. A grid where things sit and move around. But that's not the full picture. Space isn't just a backdrop. It's a physical thing. And massive objects can bend it, stretch it, and curve it. This bending of space is what we call gravity. Einstein discovered this over 100 years ago, and we've tested it many times since. And here's the key insight. If space can bend, maybe it can bend so much that two distant points connect. That connection is a wormhole. To really understand wormholes, we need to understand the stage they live in, space-time. Not space. Not time. Space-time. One combined thing. Einstein showed us that space and time are not separate. They're woven together into a single fabric. And that fabric can bend. Imagine a stretched rubber sheet. Place a heavy ball in the middle. The sheet dips. A smaller ball rolling nearby curves toward the heavy one. This rubber sheet picture is a model. It helps us see the idea. But real space-time bends in all four dimensions at once, including time. The math that describes all of this is called General Relativity. It's a set of equations Einstein published in 1915. Those same equations, the ones that describe gravity and bent space, are also the equations that allow wormholes to exist. So wormholes aren't invented. They emerge naturally from the math. The real question is, do they exist in the real universe? Before we get to that, we need to understand the two types of wormholes. Because not all wormholes are the same. Let's look at the first type, and understand why it was discovered inside a black hole's math. In 1935, Einstein and a physicist named Rosen were studying black holes. They noticed something strange in the equations. The math for a black hole had two solutions. Like a math problem where x equals both +3 and -3. One solution described a black hole pulling everything in. The other solution described a second region of space, on the other side. Einstein and Rosen called this connection a bridge. Today we call it the Einstein-Rosen bridge, the first theoretical wormhole. But here's the problem. This bridge isn't useful. You can't travel through it. Not even in theory. Why? Because this wormhole is inside a black hole. And black holes crush everything that falls in before it can reach the other side. The bridge also collapses instantly. Even a beam of light, the fastest thing in the universe, can't cross it in time. So the Einstein-Rosen bridge showed us wormholes could exist mathematically. But it also showed us they were incredibly fragile. For a wormhole to be useful, for anything to actually pass through, it would need to be stabilized. It would need to stay open. And that requires something extraordinary. That extraordinary thing is called exotic matter. And understanding it is the key to understanding whether wormholes could ever actually work. Normal matter, everything you've ever touched, has positive energy and positive mass. It attracts other matter. It curves space inward. Exotic matter is the opposite. It has negative energy. Instead of pulling space in, it pushes space outward. This outward push is exactly what a wormhole needs. It's what keeps the tunnel from collapsing. Think of it like a tunnel held open by scaffolding, except instead of metal poles, the scaffolding is made of a substance that pushes against the walls with negative energy. Now here's the catch. We've never found exotic matter in the real world. Not a single confirmed sample. But, and this is important, our physics equations do allow for negative energy to exist under special conditions. One real example is something called the Casimir effect. Two metal plates placed very close together in a vacuum experience a tiny attractive force, caused by negative energy between them. The Casimir effect is real. We've measured it. But the amount of negative energy it produces is absolutely tiny. Far too small to hold open a wormhole. So exotic matter is the theoretical requirement we know we need, but can't yet produce. That's the central engineering challenge of wormhole physics. For decades, wormholes were considered a mathematical curiosity. Interesting on paper, but not worth taking seriously as a travel tool. That changed in 1988. A physicist named Carl Sagan was writing a science fiction novel and needed a realistic faster-than-light travel method. He reached out to physicist Kip Thorne and asked, could a wormhole actually be used for travel? Could one be made stable? Thorne and his student Mike Morris worked on the problem seriously. In 1988, they published a landmark paper describing a traversable wormhole. Their model had specific, measurable properties. The tunnel had a minimum width, called the throat. And the throat had to be held open by exotic matter. Their paper was the first to ask, what are the exact conditions something would need to survive traveling through a wormhole? This was a huge step. It took wormholes from pure math and made him an engineering question. What would you need to build one? And Thorne's work opened the floodgates. Physicists started taking wormholes seriously as objects worth studying, even if we couldn't build one yet. Let's now really understand the geometry of a wormhole. How does it actually connect two places in space? Imagine space as a flat piece of paper. Point A is on the left side. Point B is on the right side. Normally, you'd travel across the paper. But now fold the paper. Bring point A and point B close together. Suddenly the 2 points are almost touching, separated only by the thickness of the paper. A wormhole is the tunnel that punches through the paper, connecting the 2 close points directly, without having to travel around. The key idea is that the wormhole doesn't move you faster through space. It changes the shape of space itself so the distance is shorter. This distinction is really important. Nothing has to exceed the speed of light. The space itself has been restructured. So in principle, you'd walk into the wormhole at one location in the universe, and step out at another location entirely. The geometry of a wormhole is called an embedding diagram. It shows two flat universes connected by a tube, the throat. This is the picture most physicists use when they talk about wormholes. Two separate regions of space-time, or even two separate universes, connected by a bridge. Now here's something surprising. Wormholes and black holes are deeply connected. They're described by the same equations. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. At the center of a black hole is a singularity, a point where density becomes infinite. Our equations break down there. Now take two black holes. Mirror them. Connect their singularities. What do you get? The Einstein-Rosen bridge, a wormhole. Some physicists think that real black holes might have wormhole-like interiors. But we've never been able to observe the inside of a black hole. In 2013, physicists Jan Maldacena and Leonard Susskind proposed something astonishing, that wormholes and quantum entanglement might be the same thing. They called this idea equals EPR. stands for the Einstein-Rosen bridge. EPR stands for a famous quantum paper by Einstein, Podolsky, and Rosen. The idea is that two entangled particles might actually be connected by a tiny wormhole, deep in the quantum fabric of spacetime. This is still an active research area. We don't know if it's true. But it suggests that wormholes might be more fundamental to the universe than we thought. Here's where things get really interesting. Some physicists believe that if wormholes exist, they might allow time travel as well. This comes from a concept in general relativity called gravitational time dilation. Time passes slower in stronger gravity. This effect is real. GPS satellites have to correct for it. Clocks on Earth tick slightly slower than clocks in orbit. Now imagine you take one mouth of a wormhole and accelerate it to near the speed of light, or keep it near a strong gravitational field for a while. The two mouths are still connected by the wormhole, but now they exist at different times. You could enter one mouth in the future and exit the other in the past. But, and here's the issue, you could only go back in time to when the wormhole was first created. You can't go back further than that. Kip Thorne and his colleagues studied this time travel question carefully. They found another problem: causality violations. A causality violation means an effect can happen before its cause. That leads to paradoxes, the most famous being the grandfather paradox. Physicist Stephen Hawking proposed a solution he called the chronology protection conjecture. He suggested that nature itself prevents time travel from ever working. His argument was that quantum effects would cause radiation to build up inside any time-traveling wormhole, destabilizing and destroying it before it could be used. We often hear wormholes described as faster than light travel. Let's clear this up, because it's one of the most common misconceptions. Einstein's special relativity says nothing with mass can exceed the speed of light moving through space. That rule still applies inside a wormhole. When you travel through a wormhole, you're not going faster than light through space. You're traveling through less space. Imagine two cities 1,000 kilometers apart. Now imagine a tunnel directly under a mountain that cuts the distance to just 10 kilometers. The car in the tunnel isn't moving faster than the car on the road. But it arrives sooner, because the path is shorter. Wormholes work the same way. So a wormhole doesn't violate special relativity. It works within general relativity, a different framework that allows space itself to be shaped. If wormholes exist in the universe, could we detect one? What would a wormhole even look like from the outside? From a distance, the mouth of a wormhole would look similar to a black hole. It would be a dark region bending light around it. But there would be differences. Light could actually pass through a wormhole, entering one side and exiting the other. It wouldn't be fully trapped like in a black hole. This means a wormhole would create a distinctive lensing pattern, a distorted ring of light that looks slightly different from a black hole's shadow. In 2019, astronomers captured the first image of a black hole, the one at the center of galaxy M87. That was a massive scientific achievement. Could we do the same for a wormhole? In theory, yes, if the wormhole is large enough and close enough for our telescopes to resolve. The problem is we don't know where to look. And we haven't found any object yet that we can say is definitely a wormhole and not a black hole. However, scientists have started developing specific signatures to look for. Gravitational wave patterns from a wormhole, for example, would look different from those of two merging black holes. So the search is on. And with tools like the LIGO gravitational wave detector and the Event Horizon telescope, we have better instruments than ever before. Let's say exotic matter isn't an obstacle. Let's imagine we somehow had a way to create and sustain it. What would actually building a wormhole require? First, you'd need to create a massive distortion in space-time. The energy required would be extraordinary, comparable to the energy of an entire star. You'd then need to carefully shape and control that distortion, keeping the wormhole mouth stable while threading exotic matter through it to hold it open. Then you'd need to move one mouth to its destination. That destination could be another point in space, possibly light years away. There's a strange problem here. To send a wormhole mouth to another star system, you'd need either another faster-than-light method, or to wait hundreds of years. Some physicists suggest a civilization advanced enough to build wormholes might send small self-replicating probes that slowly build wormhole infrastructure across the galaxy. That's deeply speculative, but it illustrates something important. Wormholes aren't just a physics question. They're also an engineering and civilization question. We're currently at zero on all three. But the fact that general relativity doesn't forbid it, that's more than just hope. That's a real starting point. Now let's explore a different angle on wormholes, one that comes from quantum physics rather than general relativity. In quantum physics, particles can be entangled. That means two particles, no matter how far apart, are linked. Measure one, and you instantly know something about the other. This connection is instantaneous, but it can't send information faster than light. Measuring one particle changes its state, but you can't control what state it collapses to. Now the equals EPR idea we mentioned earlier connects this directly to wormholes. The entanglement link might literally be a tiny wormhole in the quantum foam of spacetime. If this is true, then wormholes aren't rare exotic objects. They could be everywhere, embedded in the fabric of space at the quantum level. The challenge is that these micro wormholes would be at the Planck scale, the smallest possible size in physics. That's about 10 to the power of -35 meters. Expanding a Planck-scale wormhole to human size would require mind-boggling amounts of energy. This is one reason some physicists think macro-scale wormholes might not be physically achievable. But other physicists believe there might be ways to create large wormholes that don't require starting from Planck scale, if we understand the underlying quantum geometry better. This is one of the most exciting frontiers in theoretical physics right now, trying to unify general relativity and quantum physics into one complete theory. Let's now take stock. What do we actually know about wormholes, and what's still unknown? We know, general relativity mathematically allows wormholes to exist. That's confirmed by Einstein's equations and tested physics. We know, traversable wormholes would require exotic matter, a substance with negative energy density. This is established theoretical physics. We know, tiny amounts of negative energy exist in nature, proven by the Casimir effect. So negative energy is not completely forbidden. We know, if one wormhole mouth is time-dilated relative to the other, the wormhole could theoretically allow time travel to the past. Now, what don't we know? We don't know if wormholes actually exist in the real universe. No confirmed observation has ever been made. We don't know how to produce the large amounts of exotic matter that would be needed. The Casimir effect produces nowhere near enough. We don't know whether wormholes are stable. Quantum effects might destroy them before anything could pass through. And we don't have a complete unified theory of physics that handles both general relativity and quantum mechanics. Without that, our wormhole calculations are incomplete. So, mathematically allowed, physically unconfirmed, experimentally not yet possible. That's the honest summary of where wormhole science stands today. Even if we never build a wormhole, studying them has given us enormous insights into how the universe works at its deepest level. Wormholes helped physicists understand the information paradox. The puzzle of what happens to information that falls into a black hole. They've also deepened our thinking about the nature of space itself. Is space-time smooth? Or is it made of something, some fundamental quantum structure? These are some of the most important open questions in all of physics. And wormholes sit right at the intersection of all of them. In fact, in 2022, researchers at Google's quantum computing lab ran an experiment on a quantum computer that simulated a traversable wormhole's behavior. They didn't create a real wormhole. But they used quantum entanglement to simulate how information would travel through one, and the results matched predictions. This shows how quantum computers might become tools to test wormhole physics, even if we can't build a real one. The science is advancing. This is a question many people wonder about. Could a wormhole be big enough for a person to walk through? A spaceship? A planet? In principle, there's no upper limit on wormhole size. The equations work for any scale. A larger wormhole just requires more exotic matter to hold it open. Interestingly, a larger wormhole would actually be safer to travel through. A very small one would have extreme tidal forces that would tear you apart. Tidal forces happen because gravity is stronger closer to the center. Your feet would be pulled harder than your head. In an extreme case, you'd be stretched like spaghetti. For a human-safe traversable wormhole, the throat would need to be at least a few meters wide. And the gravitational gradient would need to be very gentle throughout. This adds yet another engineering requirement. Not just, keep it open. But, keep it open and keep it gentle and keep it stable for the entire transit time. Let's do a thought experiment. Imagine we've solved all the problems. Exotic matter, check. Stable wormhole, check. Safe size, check. What would the experience of traversing one actually feel like? From the outside, the wormhole mouth would look like a dark spherical region, distorting everything around it, like looking through an extremely curved lens. As you approach the mouth, you'd see stars and the background universe become more distorted, compressed and swirled around the edges of the opening. At the throat itself, the narrowest point, you'd be at the connecting point between two space-time regions. You wouldn't feel any physical jolt or barrier. If you looked backward from inside the tunnel, you'd see your origin universe, compressed into a circle of light at the entry end. If you looked forward, you'd see your destination universe, another circle of light at the exit end. The transit itself could be very brief, seconds to minutes, depending on how long the wormhole is and how large its throat is. Then, as you exit, you'd find yourself in a completely different part of the universe, possibly billions of light years from where you started. From the moment you entered to the moment you exited, you might have traveled what would otherwise take light billions of years, in just a few minutes. Let's bring everything together. A wormhole is a theoretical structure in space-time, a tunnel connecting two separate regions of the universe. It emerges naturally from general relativity, the same equations that describe gravity, black holes, and the expansion of the universe. It's not something invented for science fiction. It's a mathematical consequence of the most accurate description of space and time we have. For a wormhole to be traversable, for anything to actually pass through, it needs to be held open by exotic matter with negative energy. The biggest obstacles are, we don't have enough exotic matter, we don't know if stable wormholes can form naturally, and we don't have the physics theory to fully describe them. But wormholes are not forbidden. They're not like perpetual motion machines, where we can prove they're impossible. We just don't know how to make one yet. And the deeper we look into quantum gravity, black hole physics, and quantum entanglement, the more wormholes keep appearing as a central object, one that might help unlock the next great theory of physics. We started this video with a simple question: what if space could fold? And what we found is that the answer is, according to our best physics, yes, it can. And a wormhole is exactly that fold. Whether we'll ever use one, that's still an open question. But it's one of the most beautiful open questions in all of science. And we're only just beginning to ask it properly. Thanks for watching. If this made your brain stretch a little, good. That's exactly what learning about wormholes is supposed to do.